Good morning. This is the continuation of chapter 3. In the previous video, we discussed the instruction execution cycle and we discussed one example. Now let's look into the instruction cycle state diagram. The execution cycle for a particular instruction may involve more than one reference to the memory. For example, here in the slide, we have given a instruction add b comma a. So the same one instruction has more than one reference to refer the memory to get the value of b and refer the memory to take the value of a, and then the processing addition is done. And then the result is put back onto the destination b. Can you get the idea? So there is more than one memory reference is there. Sometimes an instruction may involve IO operations, not referring the memory. Maybe it refers maybe it get the data from input device or sends the data to the output device. Okay. So by considering all these details, by thinking that the instruction may have more than one reference to the memory, your instruction cycle is modified in a way to include many states. So the figure 3.6 is the instruction cycle state diagram, which includes many states starting from the instruction address calculation until the result storage, operand storage. Okay. So this is the first step, instruction address calculation. What is it? Calculating the address of the instruction, what the CPU is going to execute next. Okay. Where is the address? It is in the PC. We studied it in the previous video. PC contains the address of instruction to be executed next. Okay, so the processor refers or accesses the memory and fetches the instruction. Here it is, second step. So it fetches the instruction. So next step is the processor needs to decode the instruction. Okay, when it decodes, it tries to understand what is that instruction, where are the operands, etc., etc. So next step is it tries to calculate the address of the operand. Here in this case, in this example, in the slide, add b comma a. So there is two operands. One is the b, another one is the a. So address of the first operand and then fetch the operand. As we have multiple operand, revisit the same state. Calculate the address of the second operand, fetch the second operand. If you have multiple operands, come back, go back, come back, go back. It will be revisited. These two states will be revisited. Okay, again and again. After fetching all the operands, the next state is calculation or operation. What is that instruction? Perform that instruction. It is add here in this example. So ALU performs the addition. And after finishing the addition, the result needs to be stored somewhere, is it? So you need to calculate the address of the operand and then store the operand, the result. Sometimes you may have multiple results. So revisit the same state, calculate the address of the operand, store it. If you have multiple operands, these two states will be revisited again and again. After finishing all the storage, and the next state is, of course, go back and start the next instruction. Calculate the address and then fetch the instruction. The next topic is interrupts. All computer systems that provide a mechanism that allows the other modules, let's say the input-output device or memory, to interrupt the normal processing of a processor. Okay. So the table given in this slide, it lists most common classes of interrupts like program, timer, IO, hardware failure. Okay. So hardware failure means this kind of interrupt is generated by a failure. Maybe it can be a power failure or memory failure, memory parity error, whatever is it. Okay. IO, this interrupt is generated by the IO controller. Okay, fine. This means it signals the normal completion of an operation and it requests a service from the processor. Okay, fine. And then the timer is generated by the timer. It's a kind of a small component in the processor. Okay, this allows the operating system to perform certain functions on a regular basis, for example, every 24 hours you want to do something, or every 1 hour you want to do some disk clearance, or clear the disk, or whatever is it. Okay, so every 1 hour it will interrupt the processor. Okay, the signal, it will signal the processor, so the processor start to do some task, okay, in a regular basis, systematic way. Program. This interrupt is generated by some conditions that occur as a result of some instruction execution. For example, if you have an arithmetic operation and there is an overflow, it signals the CPU, yeah, there is an overflow, there is an error. Or for example, you are dividing two numbers, you can't divide a number by 0, that's an error. Okay, or for example, you are attempting to execute some instruction which is not possible, illegal instructions. Or sometimes there is an instruction which access the memory space, but the address is out of the space. Can you get the idea? It's outside the user's allowed memory space. Can you get the idea? So in these situations, it sends a signal to the processor. Okay, so the interrupt is generated as a result of these conditions. Okay, fine. So these are some examples, most common classes of interrupts. So these are the four classes: program, timer, IO, hardware failure. Four classes of interrupts. Okay, actually interrupts are to improve the processing efficiency. Okay, that is the main idea of the interrupts. Improves the processing efficiency. For example, you already know that the speed of the processor is different from the speed of the memory or speed of the IO devices. IO devices are slower than the processor. Even the memory is slower than the processor. Okay, fine. Assume that you have an instruction, and that instructions transfers the data to the printer. Okay, then when processor executes that instruction, and what will happen after the write operation, okay, when it executes, the processor remain idle until the printer catch up the data. Okay, fine. Don't expect that the printer speed and the CPU speed are at the same pace. No. Printer is slower than the IO devices are slower than the processor, the CPU. So, by the time the CPU executes the write operation, maybe the printer is busy with another write operation, or it has a queue of data for printing. So, the processor remains idle until the printer catch up the data that's sent. Okay. So, the length of this time, the pausing time, it may be many hundreds or thousands of instruction cycles, which is clearly a waste of processor time. Okay. So instead, processor could be doing something else. So let's assume let's look at this example. Here, there is a flow of program instructions with some examples, with interrupts, without interrupts. When there is no interrupt, when there is an interrupt. Okay, something like that. Fine. So let's assume here in the diagram, the first column, the first diagram shows execution of a program with no interrupts. There is no interrupts at all. Normal execution of the program. And in the middle column, it shows execution of a program, the flow of the program execution with interrupt. Okay. But there is a short IO waiting time. This is the one we are going to discuss. Not the third one. Third one we will see later. Okay, fine. Now let's come to the explanation. So let's assume that you have your user program. Your user program contains a series of write operations. Okay, write operation means you're sending some data to the printer for printing. So that's the write operation here. Output device. You are dealing with some output device. Okay, then assume you have your user program that has quite a few write operations. Okay, so let's look into the first column, this diagram. The first, this one is the user program. Okay, fine, user program, and there got some segment. It's numbered. Like, can you see here? There is this segment of the user program numbered 1, And this segment of the user program, it's numbered 2. And the last segment of the user program is numbered 3. Okay. So this is your code segments of your user program. This is a sequence of instructions. This segment 1, 2, 3 doesn't involve or doesn't include any write operation. There is no such write operation. Okay, can you see in between the code segment 1 and 2, there is a write operation. In between the code segment 2 and 3, another write operation. And after 3, another write operation. Okay then. So, when CPU executes this user program, it starts to execute the segment 1. After finishing the segment, you have a write instruction. It means a write call. Or to an IO program. IO program means the output device. Okay. So the IO program is a system utility. And that will perform the IO operation. Okay then. So here is the IO program. Can you see here? There is 2 segments numbered 4 and 5. Okay then. What is 4? The code segment numbered 4 is to prepare the actual IO operation. Whenever you print something, it's not just like that it will be printed. There is some task to be done first. First, you need to prepare the IO operation, input-output operation, and then your IO command. And then the actual sequence of printing will take place. Okay. So, this is to prepare the IO operation, then the IO command. Can you see the code segment 5? Code segment 5 is the sequence of instructions to complete the IO operation. Okay. It may include some setting a flag indicating that, yeah, printing is over, success, failure, something like that. Okay. So this is the code segment 4 and 5, including the IO command. This will be the write operation. Fine. Okay, let's come back. Your CPU is executing the user program. So code segment 1 executed successfully. There you have the write instruction or write operation. So what will happen? So the CPU, the CPU, then it does the IO program, the code segment 4, and then the IO command, and then after finishing the IO command, it waits and waits and waits until the printer catch up the data. Then code segment 5. Code segment 5 is the actual operation. After completing the actual operation, there will be a flag set to success or failure. After finishing the segment 4 and 5, comes back to the user program, continue the user program, which is segment 2. After finishing segment 2, can you see there is another write operation? So the same thing will happen again. So printer performs the code segment 4 and then the IO command and wait for the printer. When the printer is ready, code segment 5 will be done. And after finishing it, comes back and continue the segment 3. So in this way, CPU executes the user program. Can you see here? After the IO command, the printer will be waiting and waiting and waiting until the CPU will be waiting and waiting until the printer catch up the data, and then the actual printing will be done and then comes back to the user program. Okay. So CPU is sitting idle for certain clock cycles. Okay, fine. How are you going to save the CPU time? So make use of the CPU time efficiently. So here comes the with interrupts. Short IO wait here in the middle diagram. So what will happen here? Okay, CPU executes the user program, code segment 1. And there got a write instruction, write operation. Okay. So what does the CPU does? It prepares the IO segment 4 and issue the IO command, comes back. Can you see that arrow? CPU comes back, continue the user program. Actual printing is not done because printer is not ready. But CPU is not waiting for the printer. Can you get the idea? After setting up the device, preparing the device, after preparing the IO operation, the segment 4, issuing the IO command, CPU comes back. Can you see? There is an arrow. It comes back. Continue the user program, which is segment 2. So, while it is executing that segment 2, maybe now the printer is ready. Assume Assume in this point, there is a cross here. In this point, at this time, the printer is ready. What will happen? Can you see here? The printer sends an interrupt request signal here at this time. At this time, the printer, maybe it's ready. When it is ready, it signals the processor. What does it mean, signals the processor? It sends the interrupt signal, request signal to the processor. So what the processor will do, it will suspend the current execution. It was executing segment 2, is it? So it will stop. Stop means it suspends, puts on the hold. Okay. So it suspends the execution of the current instruction. Can you see? It goes to the interrupt handler. That is the segment 5. Okay. And segment 5 is the actual sequence of the instruction, is it? The original printing. Okay, fine. So it executes the interrupt handler, comes back. Can you see the arrow here? It was suspending the user program, segment 2. It was suspended here, is it? It continues the execution. And after finishing the segment 2, can you see another write instruction? So when there is a write instruction, again the same thing happens. So the CPU prepares the actual IO operation, which is segment 4, issue the IO command, comes back and continue the user program. CPU is not waiting for the printer. Keep it in mind. Okay. So it continues the user program, which is segment 3. Again, there is a cross here. Okay. What is the meaning of cross? Can you see here down in the picture? Cross, it says interrupt occurs during course of execution of the user program. When the execution of the user program is going on, during the time, at this point, interrupt occurs. Okay. So, at this time, this cross, at this time, maybe the printer is ready. So, the device sends an interrupt request signal to the processor at this time. So, the processor suspends the execution of segment 3, goes to the handler, perform the segment 5, comes back, continues the segment 3. Can you get the idea? So in this way, you may see the difference between with interrupt, without interrupt. When it is with interrupt, CPU time is used efficiently. Without interrupt, CPU time is wasted because CPU was waiting and waiting for the printer to be ready. You get the idea? So this is about with interrupt, without interrupt. So this is the same thing explained in this slide. So let's move on to the next slide. So when the external device becomes ready, it will interrupt the processor. This is what I said in the previous slide, is it? So when it is ready, it interrupts the processor. How? It sends the interrupt request signal. Can you see here? How it interrupts? The external device, maybe the memory, maybe the printer, maybe the input device, whatever is it. When the external device is ready, it sends the interrupt request signal to the processor, and the processor responds by suspending the operation of the current program. It puts on the hold and branching to the service routine, which is called interrupt handler. You can even call it as a interrupt service routine. So after finishing the interrupt handler, you see in the diagram, this is the interrupt handler. After completing the interrupt handler, it resumes the original, the CPU resumes the original execution. It was suspended here, is it? Because there was an interrupt occurred here. So now after finishing the handler, it comes back, continues, resumes the original execution. Okay. So this is what you need to understand. Okay then. So actually the CPU and also the operating system are responsible for suspending the user program and also for resuming the user program. Okay. So suspending the user program and resuming the user program are done by CPU and OS. Okay. So In the previous video, the part 1 of chapter 3, we saw the instruction cycle, is it? That cycle contains only two phases, fetch and then execute. That is the normal execution. But now we have interrupts. So we need to accommodate the interrupt. So interrupt cycle is added to the instruction cycle. So we have fetch cycle, we have execute cycle, we have interrupt cycle. Now three cycles. Okay, fine. So this is the modified diagram with interrupts. Okay, then instruction cycle with interrupts. So the processor, okay, fetch cycle you know already, execute cycle we know already. So the next new one is the interrupt cycle. In the interrupt cycle, processor checks. Is there any interrupt occurred? Is there any interrupt request signal? If no interrupts, then the processor proceeds to the fetch cycle, continues with the execution, whatever is it. If there is an interrupt request signal, the processor do something. What is it? Something? Again, the same thing. It suspends the execution of the current program. Whenever the CPU suspends the execution of the current program, it has to do one thing. What does it do? It saves the context. What does it mean, saves the context? It is suspending the execution, is it? At one point, it suspends. And then it jumps to the handler, interrupt handler. After completing the handler, it has to come back. It has to come back, is it? And resume the execution. As it needs to come back, it needs to know where to come back. So, it saves the context. I mean the address, where it stopped. So that it can come back nicely and execute, resume back. Okay, fine. So that means saving the address of the next instruction to be executed. It saves it. So that when it resumes the execution, it knows where to start. Fine. And it sets the program counter to the starting address. Okay then, it saves the context. Now, after saving the context, it needs to go to the handler. Okay. So, I told you in the previous classes, when the CPU is executing the instruction, PC has the address of the instruction to be executed next. So program counter needs to have the address, starting address of the interrupt service routine. That is interrupt handler. So it sets the content of the PC to the starting address of the handler. Fine. So these are the two things done. In case in the interrupt cycle, there got an interrupt waiting. If there is no interrupt, go to the fetch cycle. Okay. So the same thing, again, it's explained or compared with interrupt, without interrupt. In this diagram, in this slide, there are two diagrams. One diagram is with interrupt, one diagram is without interrupt. You can now compare it. Compare the timing taken by the CPU, okay then, for execution of the same program. So the processor now proceeds for the fetch cycle, fetches the first instruction in the interrupt handler and will serve the interrupt. Let's say if there is an interrupt, the processor fetches, because PC contains the address of the starting address of the handler. So processor fetches the instruction, the first instruction of the interrupt handler. So the interrupt handler program is generally part of the operating system. Obviously, when the interrupt handler routine is completed, what need to do? Processor needs to resume the execution of the user program. Okay, it needs to resume the execution of the user program. You already know all these things. This information is quite a repetition only. Fine. So here these two diagrams, as I mentioned a few minutes ago, you can see the timing difference. Same program is executed. One is showing the execution without interrupt, another one with interrupt. With interrupt, you may see the timing. It's very short. CPU is quite fast. But without interrupt, it takes a long time for executing the same program. Okay, fine. So you may see the timing diagram based on the flow of control. Okay. User program code segments are the one shaded in green. IO program code segments are the one in the gray color. And when you see the black one is the one the CPU is sitting idle. Okay, can you see here this long time, many clock cycles, CPU sitting idle? Again, the processor is waiting and waiting. Okay, the black shaded one is the CPU time, where the CPU waits for the IO to be ready. Okay, fine. So here you may see that the diagram, that is the B1. The B1 is the with interrupt, this diagram. The first one is without interrupt. The time is too long. When you look into the diagram 3.10b, this is with interrupt. The time required for the IO operation is relatively short. It is less than the time to complete the execution of the instruction between the write operations in the user program. So, in this case, the segment of the code labeled code segment 2 is the one got interrupted. Okay, segment 2, this one 2a, here is the interrupt, and another interrupt comes here in the 3 code segment 3. Is it fine? Okay then. So the portion of the code 2a executes half of it, and then the interrupt occurs. So processor jumps to the handler after completing. Can you see here in the here code segment 2, half of the a portion of the code segment 2 is executed. There comes the interrupt. So processor jumps to the handler. This 5 is the handler. After completing the handler, CPU continues with the code segment 2. Can you get the idea? Same happens here. When the CPU executes the code segment 3, there got an interrupt request signal. So processor jumps to the handler. After finishing the handler, processor resumes the code segment 3. Can you see here? Okay, then this is the same example of the previous slides. Okay, so it's nothing new here. Okay, then so we were discussing the interrupt. Now let's look into the multiple interrupts. What does it mean, multiple interrupt? The one we see before is single interrupt. The processor is doing some execution, the user program, and there got an external device interrupts the processor, sends the interrupt request signal. One device, one request signal. Who knows that there will be multiple interrupt? It can be, it's possible. Okay, multiple interrupts is possible. Okay, fine. A program may be receiving data from a communication line and are printing results. This is an example. Just look into the example. So the printer will generate an interrupt every time it completes a print operation. Similarly, a communication line also generate an interrupt every time there is a data comes. Okay. So in this case, it's possible for a communication interrupt to occur while the printer interrupt is being processed. That's possible. What does it mean is, so what this line is telling is, assume that the CPU is now handling the printer interrupt handler. It is now servicing the handler. While the CPU is servicing the handler for printer, maybe another device is interrupting the processor. Can you get the idea? Okay, that's the meaning. So it's possible for a device to interrupt the processor while the printer interrupt is being processed. So printer interrupt handler is being processed. So how to handle it? There are two approaches. Okay, two approaches to deal with multiple interrupts. So what are the two approaches? The first method is very simple method, disable the interrupt. Not totally. When the CPU is handling or executing the interrupt handler, assume that the CPU is now executing the handler. During this time, interrupts are disabled. When the CPU is executing the user program, yeah, it's enabled. Interrupts are enabled. Fine. Let's assume here. Can you see here? There is a user program. There is an interrupt handler X and another one Y. Okay, fine. Now, what is the idea is, when the CPU executes the user program, at this point, assume that there is an interrupt from the device X. Assume it's from the device X. So what happens? CPU suspends the execution of the user program, saves the context, save the context, and it jumps to the handler for the X, the device X. While it is serving this handler, while CPU is executing this handler, interrupts are disabled. Nobody can request or nobody can send the interrupt request signal. Okay, interrupts are disabled. Sometimes, who knows that there got some other device is planning to send an interrupt request signal. Maybe the device is ready. It wants the processor to execute. Okay, fine. So those device, for example, Y can't interrupt the processor. So because it's disabled, while the processor is executing or serving the interrupt handler, interrupts are disabled. Okay then. So CPU completes the execution of the handler and resumes the user program. The time it resumes the user program, the device Y can send the request because it's now enabled. So while the CPU is executing user program, interrupts is enabled. While the CPU is serving the handler, interrupts are disabled. That's the thing. So after completing the handler X, CPU jumps to the handler Y, completes and comes back. So this is the idea. Okay then. So the first method is disable interrupts while the interrupt is being processed. Disabled interrupt means the processor can and will ignore the interrupt request signal. It will ignore the request signal while it is executing the handler. If there is an interrupt occurs this time, let's assume it is executing the handler X and this device Y is interrupting the processor, it will ignore it. It will put it in pending, hold, okay. It will make this interrupt request signal pending. So after finishing this handler X, processor will start the handler for Y. Fine. Okay then. So when the user program is executing, an interrupt occurs, the interrupts will be disabled because when there is an interrupt, CPU jumps to the handler. The moment there is an interrupt, the interrupts will be disabled immediately. After the completion of the handler, interrupt will be enabled. You get the idea? Before resuming the user program. Right after the completion of the handler, interrupt will be enabled and then resume the user program. Okay then, so this is the idea. So before resuming the user program, the processor checks, is there any pending interrupts? Then it will start to serve those interrupt handler and then resume the user program. Okay, fine. This is one technique to handle multiple interrupts. But the drawback of this technique is it doesn't take into account relative priority. What does it mean, relative priority? Sometimes there may be some task to be done immediately without any delay. Okay, so maybe high priority jobs needs to be executed. It should not be put on hold. Okay, fine. For example, assume that CPU was executing the user program. There was an interrupt request signal from device X. So it goes to the handler and servicing the handler for device X. During the time there is an interrupt from device Y. Assume that device Y is having high priority. It's an important thing. It has to be done first. Okay, but this method doesn't care about the priority. The method says while the CPU is executing the handler, interrupts are disabled. CPU will ignore those interrupts. Right after completion of the handler, the interrupts are enabled and it will check, is there any pending interrupt? Go answer. Or else continue the user program. Okay. So here, in this case, the priority, the critical tasks are ignored for a time being. Okay then. Okay, this is for example, when input arrives from a communication line, it may need to be absorbed rapidly to make room for more input. Okay, but here in this kind of first method, it's not possible. So in case of this communication line, as you are not acting at the time needed time, the data may be lost. Okay. So that is the problem with the first method. Okay, then it doesn't take into account the priority. That means the critical task. It's not cared. Okay. The second approach is I told you that there are two techniques to handle the multiple interrupts. So the second method is you need to define the priority for the interrupts and to allow the interrupt of the high priority to be executed first rather than concentrate on the low priority. Okay, then that's the idea. So second approach is define the priority. So what is the second approach? Consider this. There is an example given here. Can you see those examples in this diagram? You may understand this one. Okay, let's look into this description here, explanation here. Assume that a system with 3 IO devices. Okay, what are the IO devices? This is printer, one IO device. It has its own routine, interrupt service routine, communication line, and then another its routine, and then the disk. So there are 3 devices are there. Each device will have its own priority. I told you a few minutes ago, communication line is having more priority. If you make the communication line pending, the data will be lost. Okay, fine. So assume this way. Communication line is having high priority. Okay, fine. So let's assume that there are 3 IO devices. What are they? Printer, disk, communication line. So the priorities are 2, 4 and 5. 2 means the priority for printer, 4 is the priority of disk, 5 is the priority of communication line. Actually, higher the number, higher the priority. 5 is the high priority device. 4 is the less priority. 2, a low priority. Okay, 4 is the medium. Okay, then assume higher the number, higher the priority. Okay then, so let's look into the diagram here. CPU is executing the user program. Can you see that? At time 0, it starts to execute the user program. Maybe at time 10, okay, at time 10, the CPU receives an interrupt request signal from printer. Okay, the priority of printer is 2. Doesn't matter. I'm receiving the first request, interrupt request, and the priority is 2. 2 is a low priority. But anyway, this is the one and only request signal. So how can I compare it? Okay, so what will happen? Printer service routine will be started to execute. The CPU go and execute the routine. Okay then. So at time at time 10, the CPU starts to execute the interrupt service routine of printer. Okay, assume at time 15, okay, at time 15, it is executing the printer service routine. The CPU is in execution. At time 15, another interrupt request signal comes from communication line. What is the priority of communication line? 5. The current device priority is 2. Printer priority is 2. Communication line, there is a new request. Its priority is 5. I told you. Higher the number, higher the priority. So you need to go and execute the high priority device. Okay, fine. So the CPU suspends the execution of the printer routine, jumps to the communication interrupt service routine. You see that? At time 15, it starts to execute that communication service routine. Okay. And after finishing that service routine, it comes back to the printer. Because it was suspended there, is it? Where you stop, go back and continue. It was stopped from the printer routine. So go back to the printer routine, continue. At time 25, it go back to the printer routine. At the same time, it receives another request. Interrupt request. Okay. From who? Device, disk. See the priority of disk 4. Disk 1 is 4, is it? The printer priority is 2. The new request priority, the disk 1 is 4. I said higher the number, higher the priority. So what to do? Go and serve the disk interrupt service routine. So printer suspends. The CPU suspends the execution, jumps to the disk routine. So start to execute, and at time 35 it completes the service routine of disk, goes back and continues, resumes the printer service routine. After finishing printer service routine, resume the user program execution. You see the sequence? Okay then. So remember which device is having high priority, that will be executed, that will be taken into account first. So this is the idea of second methodology, defining the priority. So the same explanation is given in this slide. So we'll just move on to that. Next slide. Okay. Now we finished with the interrupts. Now move on to the interconnection. In the chapter 1, we studied organization, components and their interconnection. That's the computer organization. So actually a computer consists of many components, modules. Okay. The main 3 component of the computer system is this one: processor, memory, I/O. And their interconnections, they are connected in such a way. Am I right? So in effect, a computer is a network of basic modules. There must be a path for communicating the module. There is a bus. The bus carries the data between those modules. Okay. So the connection of path connecting the various modules, that is called the interconnection structure. Okay then. So the design of the structure depends on the exchange that must be made between the modules. Like, do you send data or do you receive the data? So what is the exchange? Okay, based on the exchange, the design of the structure is determined. Okay then. So here in this side, you see three modules: memory module, and then I/O module, and then the CPU. So this 3.5 computer module suggests type of exchanges that are needed by indicating the forms of input and output of the modules. Okay, fine. Okay, let's look into the memory. So let's see the memory here. We may read data from memory or we may write data to the memory. Okay. So let's assume CPU is trying to write something to memory. When CPU tries to write something to memory, this is the control signal. Can you see? Write signal. The write signal will be on, read signal will be off. That means 0. Read signal will be 0, write signal will be 1. 1 means that is the action going to be done. So write signal 1 means the write operation is going to be done. Read signal 1 means read operation is going to be done. Okay, fine. So let's assume that write signal. Write is 1. When the CPU tries to write some data, it needs 2 things. What is the data it's going to write? I need the data. Where it is going to write? The address. Because memory is a big memory. Where to put the data? The location address. Okay then. So address comes in this bus. Data comes in this bus. So go to the address, write this data. That's it. There is no output, only input. Okay, sometimes CPU wants to read something from the memory. So as I said, read signal will be 1, write signal will be 0. So CPU wants to read the data. From which location it's going to read the data? So it needs the address. And go to the address, take the data. That data moves in this data bus, not this data bus. It will be off. There is no data passing through this line. So read means the address is passed in this address bus. Data will be passed as an output. Read means you take out. So data will go out of the memory. Here. Can you get the idea? So this is the way. This is what it's mentioned here. Okay. So this is what the design of the structure. Here. The design of the structure depend on the exchange of data. How it is made. Based on that, we will have the design of the modules. Okay, fine. The same goes with the IO module. The same goes with the CPU. Okay. Okay, then let's look into the IO. The function, it's very close to the memory. Just now I was explaining the memory. So when you look into the IO, it's very similar to the memory. Again, in the IO module, IO means what? Input and output. Okay, fine. Input means taking the data from the external device. Output means sending the result to the external device. Is it? Okay then. So again, there are two operations: read and write. Input and output. Read is input. Write means output. Is it? Okay, fine. So the read and write. Further, an IO module may control more than one external device. So we can refer to each of these interfaces to the external device as a port and give each a unique address. Each port will have a unique address. For example, printer is connected in a USB port, for example, assume. So that port will have an address. Your keyboard is connected in one USB port. Your mouse is connected in another USB port. And your monitor is connected in the VGA port. So each port is given an address. So that address determines the device. You get the idea? So in addition to that, there are external data path for the input and output of the data with external device. So the IO module may be able to send the interrupt signal to the processor. Okay then. So that is the address. Address here represents address of the ports of the devices. You know, in your system unit, there got many ports and your peripherals are connected to the ports, the port addresses. Okay, fine. Okay, when you are talking about the interconnection structure, okay, that means the main components of the computer system, the three main components: processor, memory, IO. They are connected in a way. They exchange the data between themselves, is it? So the processor, look into that here. The processor reads an instruction and data, writes out the data after it processing, and uses the control signals to control the overall operations of the system. And it also receives the interrupt signals. Okay, where you can see this, all those things. Let's go back. Better to go and see the CPU here. Okay, so you will understand that paragraph by this diagram. For example, CPU, it's trying to execute an instruction. Okay, actually, when it is trying to execute an instruction, obviously you need to send the instruction to the CPU. Instruction may have some data. For example, the instruction is add instruction, add A comma B. So the CPU needs to add A and B, put the result onto A, for example. So the instruction goes in this line and in this bus, for example. Data goes in this bus. Sometimes interrupt signals are sent. Sometimes, okay. We saw many examples in the previous slides. So the interrupt signals are sent to the CPU in this line. Okay, fine. After the CPU executes those instructions, so the result is sent here in this line. Maybe the result is send the data to memory, save the data. Okay, so the data goes here. Which address of the memory I need to save? So the address goes here. Okay, or else. So the CPU processes the data and sends the result to the output device. So which output device? Address of the output device. The address goes here and then the data, the result goes here. And then the control signal. What the control signal it's going out of the CPU is like success, failure, overflow, like error. All those things are control signals here. Let's say I'm trying to add two numbers and there got an overflow. Overflow means there is an error. So that overflow signal is sent over the control signals. So the result is a mistake, error. Can you get the idea? So that's what explained in that paragraph here. The processor reads instructions and also it reads the data. And after its performance, like calculations, it writes out the data after the processing. Okay. and it uses the control signal to control the overall operations. Okay, and moreover, processor may receive some interrupt signals also. Okay, fine. Okay, now let's look into the type of transfers. The interconnection structure, it is the communication between the three modules, the main three modules of the computer system. That got some transfer between the modules from here to there, there to here. So what are the possible types of transfers? So these are the 5 possible types of transfer. Maybe the data moves from memory to processor, or the data may move from processor to memory, or the data may move from IO to the processor, or to processor to IO, or the last one, IO to or from memory. Okay, let's see one by one. Memory to processor. What does it mean? Memory to processor. That means processor reads the instruction or data from memory. Okay. Next one, processor to memory. That means processor is writing instruction or data to the memory. Okay. This is processor is reading from memory. Second one is processor is writing to memory. And the third one is processor reading data from IO device. The fourth one is processor is sending data to the output device. The third one is input device, fourth one output device. Okay, fine. The last one. The last one is in between the memory and the IO. Here, IO module and the memory, they exchange the data without the intervention of the processor. Can you see the transfers? The number 1, number 2, number 3, number 4, processor is there. The last one, IO to or from memory, there is no mention of the processor. That means without the intervention of the processor, IO module and the memory exchanges the data from here to there or there to here. Okay, that is called direct memory access. Can you see this? DMA. In short, we call it DMA, direct memory access, DMA. Fine. Okay, so I told you that there is an exchange of data between the three main components of the computer system. So the exchange happens where? How? On the bus, through the bus. Okay, so the bus is a communication pathway connecting two or more devices. Okay, it is a shared transmission medium. This is the key characteristics. Shared medium. I don't have a dedicated bus between this and that and this. No. There is no dedicated line. One single bus, it's shared between the devices. So multiple devices connected to a bus, signal is transmitted by any one device is available for the reception by all other devices attached. That means here, if two devices transmit during the same period, their signal will overlap and then garbled. Okay then. So only one device at a time can transmit the data. That's what the control signals are used here. Okay then. So if there is one device, sends the data until until that period of time it reaches the recipient, no other device is allowed to put the data onto the bus. Okay, fine. So the bus connects major components of the computer system, that is called the system bus. Okay, actually I say bus. The bus may contain maybe hundreds of lines. Okay, each line is assigned a particular meaning or a function. Okay then. So you can say there are many different bus designs. Mean to say that we have a data bus, we have address bus, we have control bus. So data bus carries the data, address bus carries the address, control bus carries the control signals. Okay then. So let's talk about the data bus. Okay then. So data bus, the bus, I told you in the previous slide, a bus contains number of lines, is it? So that data lines provide a path for moving the data between the modules, between the devices. Okay. So there may be maybe the bus contains 32 lines or 64 lines or 188, maybe more than that. Okay. So it may contain these many lines. It depends on the architecture, how many lines are there in the bus. Okay. So the number of lines in the data bus, it's called as width of the data bus. Remember, one single line carries one bit of data. If there are 32 lines at a time, it can carry 32-bit data. Okay. So number of lines determines how many bits it can transfer at a time. If there are 64 lines at a time, it can transfer 64 bits. So width of the database is the key factor for the overall performance. If the width is so small, it needs more transfer. Can you get the idea? Let's assume that I have for example 32-bit data. My data is 32-bit. But the width of the database is two lines are there. Width of the database is 2. 2 means at a time it can transfer 2 bits. My data is 32-bit. At a time I can transfer 2 bits. So another transfer, another 2 bit. Another transfer, another 2 bit. How many times? 16 times. Can you get the idea? Because I can send only 2 bits at a time. But my data is 32-bit long. I need to break it into 16. Can you get the idea? So if a database is 32, an example is given here. That's good. If the database is 32-bit wide, the width is 32-bit and the instruction is 64-bit. My instruction is 64-bit. So what will happen? I need 2 read cycle. How many instruction cycle I need? 2, twice. First 32-bit will travel and then the next 32-bit will travel in the bus. So how many read cycles? 2 cycles. Let's move into the address bus. So the address lines are used to designate the source or the destination of the data. If the processor wishes to read a word from a memory, let's say the processor wants to read something from memory or write something to memory. Processor needs to know the location, address, is it? So it puts the address of the desired word on the address lines. The same width of the address bus determines the maximum possible capacity, memory capacity. Okay then. So width of the address bus determines the possible memory capacity of the system. Okay. Address lines are used to address the I/O ports. Don't think that address lines carries the memory address. It carries the I/O address also. In the previous slides I mentioned each I/O devices has its unique address, the port address. Okay. Higher order bits are used to select the particular module of the bus. Lower order bits are select the memory location or the I/O port. Okay. So in this way, your address bits are organized. Let's assume that on an 8-bit address bus, so this is the address 0111 and then 1111. So it might refer the location of the memory module, okay, with the 128 words of the memory and the address like 100000 and above refer to the devices attached to the I/O module. Okay then. So from the address you can able to identify that the higher order bit and the lower order bit. Higher order bit refers the module, particular module on the bus. Lower order bit, it select a memory location or a I/O port within that module. Okay, fine. And the last one, because I told you the bus, there are 3 types of buses. Data bus, address bus and the control bus. So the control lines are used to control the access to and use of the data and the address lines. Okay, fine. So data and address lines are shared by many components. So there should be some way of controlling the use of those the lines. Okay. So the control signals transmit both command and the timing information. Okay, timing signals, timing means the validity of the data. So the data will be available in the bus for 5 seconds, something like that. That is the timing signal. Okay then. Actually, the control lines include variety of signals. Like 1, 2, 3, 7 signals are given here. What are they? Memory read and write, IO read and write, acknowledgement, bus request, bus grant. What is memory write? It causes the data on the bus to be returned into the desired location. Okay, the specified location. Memory read means it causes the data from the location to be placed onto the bus. Can you get the idea? When it is write, data should be moved to the memory. When it is read, data should be moved on to the line, the bus. Can you get the idea? Reading means data comes from the memory, put it onto the bus. Write means the data on the bus goes to the memory. Is it fine? Return to the memory location. Same goes with the IO write. It causes the data on the bus to be sent to the IO port. IO read means it causes the IO port to send the data, to put the data onto the bus. Okay, fine. Transfer acknowledgement means you are telling that yeah, the data is accepted or rejected, something like that. So it indicates that data have been accepted or placed, something like that, some kind of acknowledgement. For example, if you are sending an email, I send you back a reply. Yeah, I received your email, or I didn't receive, so something like that, some acknowledgement. Okay. Bus request. Because there are multiple modules are connected to the bus. Many devices are connected to the same bus. It is a shared medium. So some device wants to use the bus to send data or to receive data. So they may need to make a request. So the module needs control over it needs to gain the control over the bus. Okay. Or bus grant mean, let's say the device is requesting the bus control over the bus. So the control is granted to that device. Okay. So bus grant means indicates the requesting module has been granted the control on the bus. So it can start to use the bus. Can you get the idea? So first of all, the device needs to make a request and then the device will be granted the bus. So the device can put the data onto it or it can start to receive the data from the bus. That's the idea. Okay then. So with this, the chapter 3 is over. Thank you.